right, ladies and gentlemen, welcome back to another round of PreAP Chemistry. We're going to take a look today at Coulomb's law and atomic structure, so that structure of the atoms will start to make some sense about why atoms do what they do. Up to this point, we've learned the general basic structure of where an atom is. We've started to learn where we're going to place our electrons in those Bohr models, and we understand there's different parts of that, those energy levels and different regions of the periodic table. So now let's start putting that to use and start predicting and using it to predict how elements are going to react, what are they going to do, what situations will it occur in, and such and so forth and so on. So the good news with this is this really just comes down to, have you ever played with magnets? And so on the screen I've got here a positive and a negative. We understand that if I have a positive and negative end of a magnet, they're actually going to be attracted towards each other and they want to pull in, right? And so this would give us our attraction. The opposite of that is true. We've got two situations there where if I have a negative and a negative, or I guess you could also have a positive and a positive, these are going to give us repulsive forces. So both of those situations would be repulsion, or repulsive, as you'll hear me say it. And so I got attraction as opposites, and the old saying, opposites attract, okay? And so now let's apply this to Coulomb's law. So we come over here, and Coulomb's law actually tells us that the amount of force, whether it be attractive or repulsive, that we're feeling here is proportional. And so we've got our force is proportional to a charge 1 times a charge 2 over a radius squared. And so Q1 is defined as my charge 1, Q2 is defined as my charge 2, R is actually just the distance between them. And so it's not anything crazy. You know, your general number sense, the bigger the top of my fraction gets, the bigger my force. Now, Q1, Q2, how I tell whether it's an attractive or a repulsive force really depends on the size of the charges, whether they're positive or negative, right? If it's a negative positive, if Q1 was positive, Q2 was negative, I would have an attractive force. If Q1 was negative and Q2 was negative, I would have a repulsive force. And if Q1, Q2 were both positive, I would have a repulsive force. So please understand, it's the sign of those Q's, whether it be positive or negative, that's going to determine whether I have an attractive or a repulsive force. The other part of this that we're going to look at is we need to understand that larger charges equals more force. And so the bigger my charges get, the more of an attractive or repulsive force they have. The other part about that is actually smaller distances. And so the smaller distances, that means my r squared would actually get smaller, and we know that the bottom of a fraction, if it gets smaller, the overall force gets larger. And so again, that is also more force. Right? So smaller charges, smaller distances and larger charges are going to give me a larger force of either attraction or repulsion depending on the signs of there. All right? So now what I'm going to do, I'm going to go ahead and draw a Bohr's model atom, and I guess let me go ahead and make that a positive. I'm going to draw a hydrogen. So I've got a positive there. I'm going to give it one energy level, and I'm going to have an electron here. Well, we know electrons are negative, and so let's go ahead and start taking a look at this and just saying, let's label it. Notice I've got right here a force of attraction. That's an F with the small a, right? That's an attractive force in this particular case. And so hydrogen has that attractive force, and the Q1, Q2 there are 1 and 1. All right, and the amount of traction is proportional to the distance. Now let's get a little bit more complicated. Let's draw lithium. Lithium has 3 protons. It has 2 energy levels. And so you'll see now, when I start placing electrons, I place 2 here, and this is the element lithium. And then I've got 1 placed on the third ring. Well, I still have, between the electrons, I still have these forces of attraction, right? Now, the second electron out here would be less attractive than the first because, again, the distance between this outer electron and the inner electron is actually larger. So my force of that second electron would still be smaller than the first. So please understand that. Now, but why I'm drawing this and what I really want to point out is the distance here, right, between these two electrons, and that would actually be a repulsive force. And so this, you know, the more electrons we stuff into these inside rings, the more they're actually going to decrease because they're going to want to push electrons away from our nuclei, all right, or from our nucleus. And so another term that I'm going to introduce here is that in this particular case for lithium, we're going to introduce a term called core electrons, right? We knew this outer one was called a valence. We've learned that before. And so now we've got valence electrons, which are on the outer shell, and we've got core electrons, which are on our inner shells, our inner energy levels, all right? And so the big thing just to remember with Coulomb's law, just to make it simple, I'm going to tell you 3 things. I need you to write them down. The number of protons matters. The number of protons matters, right? The larger that Q gets, right? Core electrons, they reduce attraction of valence electrons. Now notice I said reduce and not completely cancel out. Right? So the core electrons reduce the attraction of valence electrons. And then the last thing, the distances from the nucleus, i.e. energy levels, they also reduce attraction. Right? The further my energy levels get away from my nucleus, the lower attraction I've got for those particular valence electrons. All right? And so again, distance matters. Size and number of protons, they matter. Right? Okay, so nothing crazy. It's just like playing with magnets, ladies and gentlemen. The further you get magnets away from each other, the less attracted they are. The bigger magnets that you play with, right? The more attraction, repulsion you get there. And so don't overthink it. It really is that simple. So, but if you've got some questions, make sure you get them down, because I want to make sure that you fully understand this. This is going to be the key to understanding some trends that we're going to see on the periodic table. All right. I'll see you in class, or I'll see you in tutorials. Make sure you own the information. Make sure you get it down, and I'll see you on the flip side.